All right, good morning. So we're still talking about 12.4, tangent vectors and normal vectors. So when we left off, we had talked about how you've got a position vector, which is made up of your three components, the x of t, the y of t, and the z of t. Okay, your r prime of t, which is your velocity vector. Okay, so that's going to be x prime of t, y prime of t, z prime of t, and then your r double prime of t, which is your acceleration vector, which is x double prime of t, y double prime of t, z double prime of t. Okay, and using those basic formulas, you're going to come up with the unit tangent vector, t of t, which is r prime of t over the magnitude of r prime of t, which is just your velocity vector over the magnitude of your velocity vector. And then your n of t, you have to find the t of t, t prime of t, over the magnitude of t prime of t. Okay, now building from there. So let's say you've got this curve traveling through space. Okay, and let's say you're taking at one instant right here, you want to find the unit tangent vector. That's going to be the direction that your curve is traveling. The unit tangent vector is a unit vector, so that's one unit. The normal vector is always going to point inside the curve, or the concave part of the curve. That's your n of t, okay, which is also a unit vector, your unit normal, principal unit normal vector. Okay, now we have to talk about where does the acceleration vector lie. Okay, let's connect this to what we did in the past. In the past, we were just moving in a single direction. And let's say you were traveling in this direction. Let's say your particle right here is traveling in that direction. Okay. And if your velocity is constant, so r prime of t, or your position vector, sometimes we called it s prime, but let's just say your velocity, let's just say your speed. In this case, you're moving in one direction. So your speed is equal to 0, or let's say your speed is constant. So if your speed is constant, so some constant value, then your acceleration is 0. Okay? So that's one instance. If your speed is greater than 0, then your acceleration vector is moving to the right. So if your speed is greater than, if your speed is constant, what I want here is if your speed, your rate of change of your speed, so if your speed is increasing, let's say is increasing, then your acceleration is positive or moving to the right. Okay. And then you've got your next case, if your velocity is decreasing, so it could be positive and decreasing, then your acceleration, make sure you can see that, then your acceleration is less than 0 or moving to the left. So what we saw was if your speed is constant, your acceleration is 0. If your speed is increasing, so dv dt is positive, then your acceleration would point to the right or would be positive. If your speed is positive but decreasing, then your acceleration is moving to the left. Okay, so let's connect that up here. So if your speed is constant, you're moving along this curve, and if your speed is constant, then your acceleration vector is in the direction of the normal. Okay. If your speed is increasing, then your acceleration is going to be a little bit off to this direction. So acceleration vector would be in this direction if your speed is, let's say, dv dt is greater than 0. But if your dv dt, if your speed is decreasing along this curve, then your acceleration is going to point in this direction. If dv dt is less than 0, okay? So if your speed is constant, so if dv dt equals 0, your acceleration is in the direction of the normal. We proved that in the last section. If the speed is increasing, your acceleration goes this way. If your speed is decreasing, your acceleration is going this way. Which is kind of consistent with this. If your speed was decreasing, your acceleration goes in the opposite direction, okay? So the first thing that we see is the acceleration vector will always lie in the same plane, the plane formed by your unit tangent vector and your unit normal vector, okay? Whether your speed is increasing or decreasing or 0, okay? And what we'll also see is that your acceleration can be written as one component of your acceleration is in the direction of the tangent. One component of the acceleration is in the direction of the normal. For instance, let's say the acceleration vector goes here. You can break this down into a component that's in the direction of the tangent. So this would be a component of the acceleration that's in the direction of the tangent, plus a component of your acceleration that's in the direction of the normal. And this would make a right angle. So this can be broken down into a component in this direction plus a component in this direction, which is the direction of your normal. Okay. And what we're going to call those components, a sub t is a scalar. That's the tangential component of the acceleration multiplied by the unit tangent vector, plus the normal component of the acceleration multiplied by your unit normal vector. Okay, this thing, a of t, is your tangential component of acceleration, and this is your normal component of acceleration. So if you have a particle moving along any curve, your acceleration vector can be written as a broken down into a component in the direction of your tangent plus a component in the direction of your normal. Okay, now how do we find these things? Well, there's a couple ways to find these things. Probably the easiest way to find these things is to remember what remember our formula for a projection. Okay, remember when we said u dotted with v is equal to magnitude of u, magnitude of v, cosine of theta, and from that we were able to derive that the component projection, or the scalar projection of u onto v was equal to u dot v over the magnitude of v. Okay. Now, let's say v is a unit vector. If v is a unit vector, then this would equal component projection of u onto v would equal, would just equal u dot v. Okay, because you don't have to divide by the magnitude of v if v is a unit vector. If the magnitude of v is 1, let's just say that. Okay, so in the same way, what we can say here to simplify this is that the tangential component of acceleration is simply equal to a dotted with t. Okay, and the normal component of acceleration would be equal to a dotted with n. So you're taking, if you think of a dot product of the component of the acceleration that's in the direction of the tangent, okay, and think about what this means. This is magnitude of a times magnitude of t times the cosine of the angle between them. Magnitude of t is 1, so this is really just the magnitude of a cosine of theta. When you think about your acceleration vector and you're breaking that down into a component that's in the direction of your, let's say, your unit tangent vector, remember the magnitude's 1. Okay, so that projection of a onto the unit tangent vector is going to equal this thing, this distance, which is your tangential component of acceleration. Okay. And if we project this onto the unit normal vector, project this onto the normal vector, and this would be your unit normal vector. Remember, the unit normal vector is a magnitude of 1, so that's not going to change your projection. Project this onto here, and you're going to get this. That's your normal component of acceleration. Okay. So using these two, what we can do is we can derive easier formulas to calculate these two things. Okay. So let's do this one. The tangential component of acceleration. If we do A dotted with T, well, remember what T is. Your unit tangent vector. That was r prime of T over the magnitude of r prime of T. Or we could call it phi over the magnitude of V. Okay, so if we replace this with this, we get A dotted with V over magnitude of V, which is A dotted with V over the magnitude of V. Okay. So I'm going to write out our two formulas over here. So the formulas that are going to make these two things, the normal and tangential components of acceleration, really easy to find is the tangential component of acceleration is equal to A dotted with V over magnitude of V. Okay. The normal component of acceleration is going to be magnitude of V cross A over magnitude of V. Okay. And this one, and actually the way they write this, the dot product, they write it in the book is V dot A. It doesn't matter. I just want to make sure you're recognizing that I'm using the same formulas as the book. Dot products are commutative, so you could write it either way. Now the normal component of acceleration is this formula. We can use this formula. We're not going to derive it because in number 74 from this section, you actually derive this. So we can go over that later after you've tried that. Okay, so I just want to go over one example. Let's go over example 5 in the book. So example 5 says, okay, find the tangential and normal components of acceleration. So we're finding the tangential and the normal components of acceleration for the position vector given by r of t equal to 3t, negative t, and t squared. Okay, and remember what we're doing here. The tangential component of acceleration is going to be v dot a over magnitude of v. The normal component of acceleration is going to be v cross a, magnitude of v cross a over magnitude of v. Okay, so to find these, we need to find the velocity and the acceleration vector. The velocity vector is the derivative of the position vector. So we're going to get 3, negative 1, 2t. The acceleration vector is going to be the derivative of the velocity vector with respect to t. So 0, 0, 2. We also need the magnitude of v. So the magnitude of v is going to be equal to the square root of 9 plus 1 plus 4t squared. So 10 plus 4t squared, square root. Okay. So let's put this together. V dotted with A. So we need the dot product 3, negative 1, 2t dotted with 0, 0, 2 divided by the magnitude of the velocity, square root of 10 plus 4t squared. Okay, so this dot product, we get 0, 0, and 4t. So that's our tangential component of acceleration. The normal component of acceleration, okay, we've got to do this cross product. V cross A is equal to I, J, K, and we've got 3. The V is 3, negative 1, and 2t. The acceleration is 0, 0, 2. So this vector, the cross product is I times negative 2. The J is going to be 6 minus 0, but it's the J, so negative. And the K is going to be 0 minus 0. Okay. And then we've got the magnitude of V cross A, which is the square root of negative 2 squared plus negative 6 squared plus 0. So square root of 40 or 2 rad 10. Okay, so we've got the magnitude of V cross A, which is 2 rad 10, divided by the magnitude of V, which we have up here. Okay, square root of 10 plus 4t squared. That's your normal component of acceleration. Okay, so if you want to put this all together, remember our acceleration can be written as the tangential component of acceleration times your unit tangent vector plus the normal component of acceleration times your unit normal vector. So the tangential component is 4t over rad 10 plus 4t squared times t plus your normal component. Sorry, you can't see that. Just put the a sub t, which we found up here. Okay, put that right there. Plus the normal component of acceleration, which we found right here. 2 rad 10 over square root of 10 plus 4t squared multiplied by your unit normal vector. So you can break that down. And that's going to be really helpful in the sections and chapters to come.